All right, I want to wrap up section 3.3 by running through some examples of algorithms that run in different times. So here I have the sort of the standard common types of complexity classes. We have, or not, complexity classes isn't quite the right word. Here we have those common complexities in terms of the big O estimates. We have constant, logarithmic, linear. The n log n complexity is called linearithmic sometimes, or other times you might see log linear. We have quadratic. I didn't do any other powers here, but then we have exponential and factorial. So I just wanted to give some examples. Some of these are kind of like real world examples, just to wrap your head around what it means. So an example of a constant time operation would be like washing hands, right? Washing hands takes a certain amount of time, right? You sing happy birthday twice and then you're done, right? That's a constant amount of time. Other constant operations, like I've mentioned before, are assignments, additions, and comparisons. Logarithmic, right, is looking up a word in the dictionary. When you look up a word in the dictionary, you just open the dictionary and then you check to see what page you're on, and you think, is the word before or after this page in the dictionary? And then you flip either backwards or forwards, right? And so that's essentially implementing the binary search algorithm, right? You're opening and then you're either going back or forwards. And it's kind of like a random version of binary search, but that is like a log time algorithm. So binary searches are common example of a logarithmic algorithm. For linear, linear would be like reading a book, right? It takes all n pages and it's some maybe constant time for each page based on how fast you read. But that would be a linear algorithm. Linear search is something we know is linear. Also, finding a maximum or a minimum is an example in the textbook, which is a linear algorithm as well. So for linear arithmetic, an example of this would be the merge sort algorithm. Merge sort, I do not believe is in the textbook, but this is a sorting algorithm which is a little bit better than bubble sort. Bubble sort and insertion sort actually are both n squared, big O of n squared. Bubble sort and insertion sort are big O n squared. Most sorting algorithms are either quadratic or linear arithmetic, and the best ones known are linear arithmetic. So merge sort is a pretty good one. So sorting a deck of playing cards is kind of like that. It's possible to sort a deck of playing cards with the same approach as merge sort. An example of the quadratic besides the bubble sort is double checking a shopping list. So what I mean is if you've gone around the grocery store and you have all your stuff in the cart, you could go down your list and say, do I have milk? And then search through your cart to see if you have milk. Okay, I have milk. Do I have cheese? Search through your cart. And you might look at everything in your cart, and technically you have to look at things in your cart until you find the cheese, right? And then say, yes, I have the cheese. Do I have the tomatoes? Yes, I have the tomatoes. Do I have this? And so you're going down your list, and every time you go down your list, you're also checking all the things in your cart to see that you have that thing. And so generally you're not going to check everything in the cart because you're going to see it pretty quickly. But worst case scenario, you have to look at everything in the cart before you find the thing that you're searching for. So as a worst case runtime, double checking your shopping list is going to be a quadratic big O of n squared algorithm. And then for the last two, exponential, I was kind of struggling to find examples of these things that we have covered already. I think later in the semester you're going to encounter more algorithms that are exponential, especially when you get into dealing with graphs and trees, and maybe when you talk about we're not going to get to Turing machines later in the semester. But one of the teams will be studying Turing machines. But for now, an example of a big O of 2 to the n, an exponential time algorithm, would be finding a power set. Because the number of elements in the power set is 2 to the n, right? Where n is the size of the original set. So when you are going through and writing out the entire power set for a set like XYZ, the algorithm, the process of doing that would be big O of 2 to the n. All right, and that would in fact be the exact number of different sets you have to write out. So the last example is for factorial. An example of a factorial time algorithm is this sort of joke algorithm called Bogo Sort. This is an algorithm that was designed to be the worst sort possible. it takes in as its input, A1, A2, dot, 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 up to AN, a list, okay? And it wants to sort it. It wants to sort that list into order. So it uses a while loop. It says while list is not sorted. Okay, so you have to have some way of checking to see if the list is sorted. Okay, so while the list is not sorted, what you do is you randomly permute the list. And that's the Bogo sort. So this is a joke because it's a terrible sorting algorithm. Essentially, it's like saying, take your list. Is it sorted? No. Well, then randomly shake it up and then look at it again. Is it sorted? No. Randomly shake it up again. Is it sorted? No. Then keep randomly shaking it up and just like mixing it, like sort of shuffling it until it's sorted. Right? If you sit there and shuffle a deck of cards until it's sorted, that's Bogo sort. Now, there's two ways of looking at Bogo sort. If this is a true random process, is this random permutation is truly random, like shuffling a deck of cards, right? Then actually, big O of n factorial is just its average runtime complexity. Its worst case complexity is big O of infinity, because you could go on forever and never sort the algorithm, so sort the list, right? So it's big O of infinity if this is a truly random process. But a lot of randomizing, a lot of like algorithms to randomize a set or a list use some kind of a seed. And if you have some kind of like a seeded algorithm, then what it does is every time you run the algorithm, it's going to give you a different permutation. And so if this process of randomly permuting the list is actually running through all the different possible permutations of the list in some sort of a way where you're gonna do all those permutations, you're gonna run through all the permutations before starting over. Well, then in that case, the worst case is actually big O of n factorial. So it kind of depends on how exactly you're doing the randomizing. But anyway, that's an example of Bogo sort. And why is it n factorial, by the way? Well, the reason it's n factorial is because n factorial is the number of different permutations of a list of length n, right? We learned that back when we were talking about counting in chapter 6. The number of ways to permute this is n factorial. So worst case is you run through all the different possible permutations, and the very last one is the one that puts them in order, right? Worst case scenario. So there we go.